Yeah, welcome back. So we are going to continue with the new series we just start, which is a concept-based lecture. Right. Our topic for today is Faraday's first law of electrolysis. So that's what we're going to be dwelling on. Right. So as other lectures, we will start with an outline. Right. So you have a glimpse of what we will be treating today. Okay. So first off, okay. So we have a brief introduction. All right, brief introduction of what electrolysis is, right? We're going to like set a framework. Do you get? Also, we are going to treat electrolysis. We just talk about what electrolysis is all about. All right. So we also talk about electrolytic cell. All right. So we're going to also talk about yeah, the main focus for today's lecture, which is Faraday's first law. Right. So after that, we're going to now treat questions, and questions. Right? So, are you ready for this? Ensure you are with your notebook. Yes, let's begin. All right. So, first off, right? First off, we have to understand where electricity is coming from, right? What concept is it under? Like, what topic, what concept is electricity under? I get it. That will give us a framework, right, or an idea of what it actually means. I get it. Okay, now, just like everybody in life came from a particular background, you get a mango fruit, right, was once on a branch, right? So you get the gist. So now, electrolysis is actually under a reaction, right? It's also under a reaction. So it makes me starting from this part, chemical reaction, chemical reaction, right? So I will in a very short while now, I'll tell you how chemical reaction is linked to electrolysis. Exactly. So now, chemical reaction, we have different types of chemical reaction. We have, I'm not going to dwell on everything. I will focus on only one of them. I'll focus on only one of them, which is the redox reaction, which is the redox reaction. All right, so when you say redox reaction, what exactly do you mean by redox reaction? So redox reaction is divided into two. We have like it's divided into two parts, right? Which is the reduction part of it and what the oxidation part of it. Exactly. So we have the reduction part of it and the oxidation part of it. So in simple terms, I can just say redox reaction is simply a reaction that comprises or that undergoes reduction and oxidation. Exactly. So basically, that's the main. Now, when you say redox, now we know that it's redox, reduction, and oxidation. And for people who do not know, for students who are currently watching this and don't understand what this term mean, um, first off, what does redox reaction mean? When you hear redox reaction, what comes to your mind? It's a redox reaction simply a reaction that involves electron transfer. So, redox reaction is like a business, right? So it's like a business, just like every other, let's say, an eatery now. What it does is prepare food for you to eat, right? So redox reaction, her own business is what electron transfer. So it's actually a reaction that involves what electron transfer. Now, under redox reaction, right? Under redox reaction, we have a special type. We have a special type which is under this category. We call it electrochemical reaction. Electrochemical reaction. All right. I honestly like making things really easy. Not only because I teach, also for myself, right? Also for myself. So now, electrochemical reaction. What comes to mind? Now let me break it down. Now, this more like talks about electric, let's say electric current, right? This is more like an electric current. So this is like the chemical part of it. The chemical part of it. So maybe what this is trying to tell us is that electrochemical reaction is a reaction that 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 allows the interaction between electric current and chemical energy. Yeah, maybe, maybe. You get that's what I'm having in mind. Exactly. Or simply a chemical reaction that produces electric current, or an electric current that gives rise to chemical reaction, vice versa. But now, one was to standardize this now. To standardize this, electrochemical reaction, right, is of two types, right? So one occurs in electrolysis, electrolysis, while the other occurs in electrochemical cell. Electrochemical cell. All right. This is good. All right, this is good. Now, these these special cases of electrochemical reaction are more or less opposite of each other. Yes, they are more or less opposite of each other. So in today's lecture, we are just treating a concept under electrolysis. In subsequent lecture, we're going to treat electrochemical cell in great details. We're going to talk about like Lancer cell, we're going to talk about the Daniel cells. Just stay tuned. Ensure you click the notification bell, right? So you don't miss any one. All right. So basically, this is it, right? So we have electrolysis and we have what electrochemical cell. Now, electrolysis. Hope you're following. Right, electrolysis. What does electrolysis mean? Just like I say, I like breaking things down. I like ensuring that I flow with what I'm saying. So this is more like an electric current. Electric current. And lysis means breakdown. Lysis means breakdown, right? Breakdown. Something like that. Breaking. So it means that electric current brings about breaking down of something, or yeah, decomposition or something like that. That's what electrolysis kind of mean based on the name, judging from the name. How correct? How true is this? How true is this? All right. Formally, electrolysis is defined as the process whereby a chemical decomposition occurs when an electric current is passed through an electrolyte. Let me come again. Electrolysis is a process whereby a chemical, right, whereby chemical decomposition occurs when an electric current is passed through an electrolyte. All right. So this is in line with what I explained, right? You don't need to cram it. You don't need to cram it. You don't need to cram anything. Just have to understand. Now, so you have to note that during electrolysis, electric current is used to bring about electrochemical what? Reaction. Sure you get. Now, I said that it can be vice versa when I was trying to decode what this means, right? So I can say it can be vice versa. All right, so in electrolysis, it's actually electric current that gives rise to chemical reaction, right? But in electrochemical cell, it's actually chemical reaction that gives rise to electric current. That's what you need to know. And there's this question that is actually very common. It's relating to Gibbs free energy. Now, Gibbs free energy, we have delta G, Gibbs free energy. All right, so we have Gibbs free energy. What do you understand by this? And in Gibbs free energy, is it positive in electrolysis or is it negative? All right, now you have to know when it's positive and negative. Now, when a reaction is non-spontaneous, Gibbs free energy is positive. But when a reaction is spontaneous, Gibbs free energy is what? Negative. Right? This is something you must know. You must know. Now, is electrolysis spontaneous? We don't know. We don't know. We really do not know. First off, what does spontaneous mean? in this case, when they say spontaneous, what did they actually mean by spontaneous? Spontaneous means that it occurs by itself, right? It does not attract or does not need external support, external assistance. Do you get it? It does not need external assistance. It does not need external support. Hmm? So that is something you must know. So, but now, does electrolysis need external support? Yes, it does. Electric current. Yes, no, it needs. So it means that electrolysis is a non-spontaneous reaction. Is what? Non-spontaneous, right? Is non-spontaneous. We must know that. We must not forget. Since it's non-spontaneous, it means that the gauge free energy is what? Positive. Do not forget this at all. Do not forget it at all. All right, let's move on. We have no time. Electrolytic cell. Now, what do you understand? Because like first principle, right? What do you get? What do you understand by electrolytic cell? So most likely you will say it's simply where electrolysis occur. Yeah, in simple terms, it's really what where electrolysis occur, and you're not wrong, right? So electrolytic cell is simply a medium by which electrolysis what takes place. As simple as that, right? As simple as that. It's simply a medium whereby electrolysis what takes place. All right, so we have a setup, electrolytic cell, right? So it's very simple. Okay. All right, so these are the electrodes. These are the electrodes. Okay. All right. All right, so these are the electrodes. All right. Okay. All right, so this will be the negative, right? This is the positive, positive. Okay, so I will explain this. I'll explain this. So do not worry about yourself. Do not worry. First off, the constituent, right? We defined it. We defined what electrolytic cell mean. So what's the constituent of electrolytic cell, right? Right. So we have two major constituents, like what makes up electrolytic cell, right? One is the electrode, and the other is what electrolyte. These are the two major components. These are the two major components. Now the electrode, right? The electrode are conductors. Are conductors. So and conductors are basically metals, right? And carbon, graphite, which is which is an allotrope of carbon, right? So electrolytes are compounds. They are not they are not metals, right? They are compounds. Exactly, they're compounds. And what are they like? What are some of the examples? We have NaCl, we have Na2SO4. These are few examples of compound. So they dissociate, right? They dissociate when electric current is passed through it. Is that clear? Okay, but I want to set something straight here. Now we do hear cathode, anode, and the likes like that. What exactly do they mean? What do they mean by that? Cathode is simply where electric current leaves the cell, right? So electric current in this chart, in this diagram, electric current enters into the electrolyte via the anode, right? Via the anode, right? And leaves via the cathode, and leaves via the cathode. Exactly. All right. So just know that cathode anode. Basically, you we will not be asked more than that. So this representation here is the battery. That's battery, right? So electric current is entering into the electrolytic cell. This is the electrolyte. These electrolytes, right? All right. So basically, this is what electrolytic cell is all about. All right. So let's go over to Faraday's first law, right? Faraday's first law of electrolysis. Faraday's first law. Now, every good student will ask, okay, is this the only law that Faraday proposed? No, it's not, right? So, but there are two major laws, right? Which is the first and second law, right? Well, in subsequent video, we're going to dwell on the second law, right? It's a little bit, it's simple. I definitely make things simple, but it's a little bit technical compared to first law, right? So this Faraday first law is to set the stage, right? To ramp up your understanding, right? Okay. Now, what's Faraday's first law? Now, I do not like cramming. I just like knowing something, right? So it's easier for me to flow. Now, Faraday's first law, we have to just know that is M directly proportional to what? Q. It's just this, right? Whenever you remember Faraday's first law, remember MQ, like just literally, because you can you can even write out you can even state the law based on this mathematical equation. Exactly. Now, let's state this now. Now, the first Faraday's first law of electrolysis states that the mass of an element liberated or deposited during electrolysis is directly proportional to the quantity of electrolysis that passes through the electrolyte. Do you get it now? So now let's solve from here. This mathematical equation. Let's get something off straight here. So we have M is equal to ZQ. This shouldn't be difficult to understand, right? We're trying to remove the proportionality, right? The disproportionality, and to remove it, we have to introduce a constant, and the constant which you've introduced is denoted by Z. Do you get that now? All right. So we can go as far as saying that, okay, since Q is equal to IT, so we have M is equal to ZIT. Like, very clear, very simple. Is this clear? All right, good. So this is basically what you need to have in your fingertips to proceed. And also, most times, JAM might not ask you some questions that are like this simple, you guys are big boys and girls. So they might go as far as trying to link it to STP. They can try to link it to molar, to mole, to like to concept you actually learned in stoichiometry. So you have to be very, very smart. Right? You have to be very, very smart to be like, okay, oh, this has to come in. Okay, this has to come in, right? So now we have STP, right? We have Avogadro's constant, Avogadro's Avogadro's constant. You have to know that, which is 6.0, like 0.6.023. You get. We have to know that. You have to know Faraday's constant. Faraday's constant, right? 1 Faraday is equal to what? 96,500 coulombs. You have to know this. We have to know the volume, right? The standard volume. What's the standard volume, right? Is 22.4 dm3. Exactly. So these are stuff you need to have your fingertips. Though most questions that you'll be given, right, will have this constant there. Exactly. But you can't predict. Know them. Just know them, right? So let's go into questions. Are you ready? Let's go. Yeah, we have the first question of the day, which is what the first question of the day. So a current 0.72 ampere, right, where was passed through a solution of an electrolyte for 3 hours 20 minutes. Calculate the quantity of electricity passed. Look, do not try to deceive yourself. To learn, you have to participate, you have to be active, you have to interact. So now pause this video. Yes, you pause it. Good. Go get a book and write. right? Go get the book and solve, right? When you solve and get your answer, wait, continue the play the video back so that I can explain to you. Okay, let's solve. First off, as a principle, right? Whenever you're solving any question, like any question that requires any calculation questions, ensure you write out your parameters. It's really important. Your parameters are very, very important. Okay, so your current is equal to 0.72 ampere, right? So we have time to be equal to 3 hours 20 minutes. Exactly. So we have 3 hours, so we have 3 times 60, exactly, times 60 again, exactly, in one box, plus 20 times 60. I hope you're getting it. So 3 times 60 times 60, please help us with your calculator. 10,800. Very correct. What of this? We don't need a calculator for this. This is 1,200, right? So 10,800 plus this should give you somewhere around, yeah, 12,000 seconds. 12,000 seconds. So this is what it should give you, right? So we are trying to get the quantity of electricity power, which is Q. And before now, I've explained to you that Q is actually equal to IT. Is that clear? Now, so just multiply. We are going to be getting 0.72 ampere times 12,000. So, like, easy peasy, right? Is that simple? Is that simple? So you're going to get 8,640 if you click this into your calculator. So we're done with this. Let's go out to the next question. Question number 2. Now, determine how many moles of electrons are transferred when 4,825 coulombs 4,825 coulombs of electricity are passed through an electrolytic cell. And we've been given a constant, 1 Faraday is equal to 96,500 coulombs. Okay, so now to determine the amount of electrons transferred by 4,825 coulombs, we have to get the logic. Okay, how are we going to approach this? Yeah, how can we approach this to get the correct answer? Okay, now, know for a fact that most times you don't really need to know the formula. You just need to know how to apply them. You need to know how to relate them. Like for this now, this is how many moles we're told to find mole, right? And we've been given Faraday, something around Faraday, something around coulombs. So this is a mole coulomb, right? This is a mole coulomb what relationship. Is that very clear? This is mole coulomb what relationship. Okay, now by definition, we know that 1 Faraday is equal to 1 mole of electron, right? Meaning that if we have an equation whereby we have, like, let's say this plus electron, right? We can say that this electron, because there's one electron here, is 1 Faraday, right? It's logical, right? And it has been proven to be true. So this means that 96,500 coulombs, is that clear, is equivalent to 1 mole of electron. Hope you all agree with me. Okay, now, if this is equivalent to 1 mole of electron, 4,825 coulombs will be equivalent to how many? We really do not know, because that's what we were asked to find. We were asked to determine the number of moles of electron, right? We really do not know, right? We really do not know. Okay, now, cross multiply, right? So we have 4,825 times 1 is equal to x times 96,500. So divide both sides by 96,500. 96,500. So x is equal to 4,825 divided by this. Please help me with your calculator. Please help me with your calculator. Alright, good. So we're going to get 0.05 mole, right? So I've 0.05 mole. Exactly. Do you have any question on this? It's very clear. I don't think any of this should confuse you. Now, let me know what, so let me just go over it again so you can get very well. Now, determine how many moles of electrons are transferred, right? So we know that our electrons transferred. We know, yeah, one of our electric current is passed through, right? Definitely, definitely, uh, uh, um, 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 certain amount of mole of electrons are transferred. So now, by standard, by standard, 96,500 coulombs, right? 96,500 coulombs, right, will actually lead to the transfer of 1 mole. Oh, no, it's actually equivalent to 1 mole of electron, right? So 19,500 coulombs is equivalent to 1 mole of electron. Now, so 4,825 coulombs is equivalent to how many moles of electron, right? We basically just cross multiply and we'll get our answer. Okay, now let's see the next question. We have a lot of questions to go. Now, calculate the amount in moles. Calculate the amount in moles of aluminium that will be deposited by passing 4 Faradays of electricity. So 4 Faradays of electricity through solution of aluminium salts. All right, so first of all, we have to write our equation. We have aluminium here, right? So we have 3, right? Give us Al basically. So this is a mole. There's a mole Faraday relationship. So this is a mole Faraday relationship. Okay, so 3 Faraday, right? Liberate 1 mole, right? 3 Faraday liberate 1 mole. So now 4 Faraday will liberate how many mole? X. We really do not know. X mole. Okay, so cross multiply. We have 4 Faraday is equal to X times 3 Faraday divided by 3F. Wow. So X is equal to 4 divided by 3, that should be 1 point something, 1.33 mole. Do you get? You might be wondering why I didn't include Faraday, maybe. I don't know, but F you cancel F. Exactly, X here is talking about the mole. Is that very clear? Alright, so let's proceed. What quantity, sorry, a minute. What quantity of electricity will liberate 0.125 mole of oxygen gas during the electrolysis of dilute sodium chloride solution? Okay, now you might be wondering, okay, where exactly did the oxygen come from? Right, where exactly did the oxygen come from? Now we have to take note of something very peculiar here, which is solution. Now solution denotes that water was present, and whenever electric current is passed through electrolytes, right, we expect the composition to undergo, right? So we're going to have a reaction like this. We're going to have a reaction like this. Okay, all right, plus E. So we have, okay, right. So this is like for electron. So this is the reaction we're going to actually have, and it means we have 4 Faraday, right? 4 Faraday associated with 1 mole of oxygen, right? So meaning that 0.125 mole we will be associated with how many? X. Exactly. Right. So what quantity of electricity? Meaning we're basically looking for what? For Q. Okay, since we're looking for Q, it's not appropriate for us to just we can still go through that part. Let's go through that part. Let's go through that part. Okay, let's go through that part. Let me just get X. Let's just get X first. So X is equal to 0.125 times 4 Faraday, right? So this X here is the same thing as Q, exactly. So 0.125 times 4 times 96,500. Mutu, please help me solve this out. What was the answer? Okay, so 48,250 coulombs. So these are our final answer. Is that clear? All right. So okay, let's go to the next one. How many Faradays of electricity are required to deposit 0.2 mole of nickel if 0.1 Faraday of electricity deposited 2.98 gram of nickel during electrolysis of its aqueous solution? Alright, so to calculate the number of Faraday required to deposit 0.2 mole of nickel, right, we have to know what is given. So we're given that 0.1 Faraday, right, deposited 2.98 gram. This is a fact, right, based on the question of nickel, yeah, of nickel. Okay, so now we have to first of all convert this to mole because we are actually dealing with mole here, right? Because look at this, exactly. So we have to like try and just get out the mole. So now a mole is equal to mass over molar mass. Please know this. So mass is equal to 2.98, right? The standard molar mass is what is given here, which is 59. Is that very clear? So please help me with calculator again, please. Yeah, 2.98, yes, divided by 59, yes. All right. So 0.0505 mole. Yes, mole. All right. So we know that 0.1 will give this. Is that very clear? So we're now right. We're trying to get how many Faraday. So X Faraday, right, will give 0.20. Do you get like X Faraday? So um, cross multiply. We have X is equal to 0.1 Faraday times 0.2 divided by 0.5 0 oh sorry 0.0505, right? So please just click it in the calculator. You should get the answer straight up. Yeah, that is 0. What 396 Faraday. So approximately is what 0.4. Like, do you get it? Do you get it? So it's as simple as that. All right, so now we are asked here a very simple question. I intentionally included this question, right, to serve as a channel to what is coming up front. Now, one Faraday of electricity will deposit 1 mole of what? Now, lead. We have lead. Lead is denoted by Pb, and we have a 2 plus. Is that very clear? So we have like two electron. Okay, now I think it's just a lot of students confused, like they don't really get why we are adding electron to this part. But when we come to non-metals, we don't do that. Yes, I should set it now. No, now whenever I see something like this, it's just like a guy shouting, hello guys, I am deficient of 2 electrons. Please help. Like, please help. Like, I'm deficient of 2 electrons. Right? So here's this guy coming to the rescue. Right? So is this guy is coming to the rescue, adding 2 electrons, right, to neutralize it to become what? A whole atom. Do you get, like, basically what is really happening here? But now in non-metals, let's take for instance chlorine. Now chlorine is shouting, I am full, guy. I'm so full currently, right? So you don't expect electron to be added to this part. It has to be added to the opposite part. If its intention is to get neutralized, if its intention is to become an atom. Okay, because currently is an ion. Exactly, current is an ion. So to become an atom, it has like uh, you know, okay, it's definitely an atom, but to become neutralized. Let me put that way. Let me not confuse you guys. Okay, so we have electron here, right? Plus what? Chlorine. But now chlorine does not exist as a monoatom. It's actually is diatomic, right? It's diatomic. You should know. Okay, so chlorine we're going to have like two. Yeah, again, you have like two and two here. Exactly. So here. So like basically these how it exists. Basically this how it exists. Yes. So let's continue. Aluminium. Aluminium. So aluminium is denoted by the ion is Al3 plus. So like we have 3 electrons and to aluminium. So we have the next one, iron. So iron is a big bro. It exists in two forms, which can either be EF2 plus or EF3 plus, and the same thing applies, right? Same thing applies. Same thing applies, and silver. Well, silver. So silver is like silver is this guy. So silver is have only one. Um, it just needs to gain one electron, right? So to controlize. So now the asks a simple question here that 1 Faraday of electricity will deposit 1 mole of. Now, based on what I explained in the previous example, now if the first one, it means that 2 Faraday is needed to deposit 1 mole of lead, right? This one means 3 Faraday is needed to deposit 1 mole of aluminium. Do you get? Now this one means 2 or 3 Faraday is needed to deposit 1 mole of iron. But in this one it means 1 Faraday is needed to deposit 1 mole of silver. So what's the answer? You know it already. What's the answer? Correct. Silver. Do you get it now? So it's as simple as that. Let's go to the next one. Which of the following ions require the largest quantity of electricity for discharge at an electrode? So now pause the video. Good. Oh yeah, try 7 it. Try 7 it and see if you can actually get it. Now, the same method I used for the previous example, I'm going to use for this one too. Aluminum 3 plus, right, plus 3 electron. We give this exactly. Okay, we have the second one, that's for B, this for A. For B now, for B we have this plus 2 electron to give us copper. Alright, so we have sodium electron to give us sodium, and the last one we have chlorine. Like, am I to add electron here? No, of course, it's going to be at the other side. So yeah, exactly. So we have to balance it. If there are two chlorine atom, so we have to put 2 chlorine atom here. So 2 times that is 2 electrons. Exactly. So now this is the first question I asked. 2 moles of aluminium. So we have 2 moles here. So multiply through by 2. So it becomes 6, right? So it becomes 2, right? So it means this needs 6 Faraday. That's what this means. Now the next one, they say 2.5. So 2.5 means I'm going to multiply through by 2.5. So it's going to become 5, to become 2.5. So here it was 5 Faraday. Exactly. So for chlorine, to multiply through by 3, 3, 3. So this is like 3 Faraday. Okay, what was this? We have 4 moles of chlorine. So we have 4 moles. If there is 4 moles here, meaning that we just have to multiply through by 2, right? We multiply through by 2 becomes a 4, right? Here it becomes 4, it becomes what? 2. Okay, this was like 4 Faraday. Exactly. Now, this stuff here means what? Charge. Exactly. It means quantity as a charge. It means quantity of electricity. I take that back. It means quantity of electricity. Is that very clear? Okay. Now, since it means quantity of electricity, right, we are going to say 6 times F, which is 96,500, 5 times 96,500, everything like that. Now, which one do you think will have the highest? We require the largest quantity of electricity. Which one? Exactly. A. A is correct. Exactly. 6F. That's a whole lot. That's a whole lot. All right. So let's go to the next question, which they say a current of 0.2 ampere. A current of 0.2 ampere flowed through silver trioxynitrate 5 solution during an electrolytic process, right? That lasted for 30 minutes. Calculate the mass of silver deposited. Calculate the mass of silver deposited. Calculate the mass of silver deposited. Okay, we know for a fact that this is the equation involved, right? Meaning 1 Faraday, right, deposits 108 gram, right? So this 1 Faraday is like 96,500. Exactly. Exactly. Okay, now we have our I at 0.2 ampere. Exactly. What about IF at 0.2 ampere? And what about time at 30 minutes? What about time at what? 30 minutes. So it's 30 times what? 60. Is equal to what? 6 times 3. 18, 0, 0 seconds. So Q is equal to 1800 times what? 0.2. Please help me with calculator, please. Yeah, what was the answer? Or let's just get it straight. Yeah, let's just get it straight. So we have like 96,500, right? 96,500 to give 108. Now 1,800 times 0.2 will give us x. Cross multiply. We have I'm sorry, so we have like x is equal to 108 times 1,800 times 0.2 divided by 96,500, right? So what's the answer? Just click into the calculator here. You should get the answer straight up. What's the answer? Yeah, correct. 0.4. Right, 0.4 gram of silver. So 0.4 gram of silver. I hope I'm not missing anything. Yeah, 0.4 gram of silver. All right, so let's proceed. Let's proceed. Let's proceed. Okay, so this is a very interesting question. 1,400 centimeter cube, 1,400 centimeter cube of oxygen was liberated at STP during an electrolytic process lasting for 4 hours. So, lasting for 4 hours. Okay, time is 4 times 60 times 60. Okay, calculate the amount of current I that passed through a solution. Okay, okay. Okay, so now to find current, right? First, we have to find the quantity of electricity that to liberate 1,400 centimeter cube. That's the first thing. That's the first thing we have to find. Exactly. And since we're talking about oxygen gas, it means that we have to introduce this our big brother here, right? By now you should be you should have crammed it. I don't know, like they love this question a whole lot. They love it. So I don't know, just learn it, yeah. Just learn, just know it that way. Do you get? So this is like 4 Faraday. This is like 1 mole. Right, 1 mole is equal to um 22 22,400 centimeter cube. Ticket. You might be confused and be like, yeah, you told us 22.4 dm cube now. Like when you were starting, yes, it's the same thing, right? It's the same thing actually. You have to convert centimeter cube to dm. What do? You divide by 1,000 now. I've been now for physics. Yes. So you divide by 1,000, you should be able to get your 22.4 dm cube. Yes, now. Yes, now. It's very simple now. Yes. Okay. Now, so this is like basically the framework you have to work with. The framework you have to work with. So meaning that so from this equation, 1 mole of oxygen requires 4 Faraday, right? 1 mole of oxygen requires what? 4 Faraday. You have to know that at STP, right? So 1 mole, I said, is also equal to this. So meaning that 1 mole is also known as 22,400 centimeter cube, right? 22,400 centimeter cube requires what? 4 times 96,500. Exactly. I hope you this 96,500 is as this. Sure you get. Alright. So please just take note of that. Now, from the equation, we have our main goal, as I told you, is to find what Q first. After finding Q, you can now like get use Q equals to IT. I hope you are feeling with me. Please do not be confused, please. Please, yeah. So we have 1,400 centimeter cube, right, will give us x. So x is equal to 4 times 96,500, right, times 1,400 divided by 22,400. Exactly. Right, so just click this in the calculator. Please help us out, please. Yes, 4, yes, times 96,500 times 1,400. Yes, divided by 2,000, 22,400. What do you get? 24 125. Yeah, 24,125 coulombs. So Q is equal to IT. 24,125 is equal to what? I divided by 4 times 6 times 60. Right, so our I is what? Just click that into your calculator too. You should get your answer straight up, which is 1.68 amp. Exactly 1.68 what? Ampere. So hence the current path is 1.68 what? Ampere. Easy peasy. All right, so now next question. So a current of 3.8 ampere passes I equals to 3 yeah, a current of 3.8 ampere passes through, right? This is technical. I'm sure most of you will post video like well, that's what I'm here for, Isha. So the current is 3 ampere, right? So we have like our mass to be like 26.6 grams, right? Molar mass to be like 119. So our mole, it would like most likely be 26.6 gram divided by 119, like this is rubbish. Now, but we're to find something interesting, oxidation state. Now, most times we know the oxidation state. Most times, like we already know is one, just one, aluminium 3 plus. But this guy, we don't really know what the oxidation state of tin is, right? But yeah, we don't really know what the oxidation state of tin is. It's a transition metal and it varies. It's not like very, very constant. It's like it varies depending on the state. So now we have Sn, right? N plus. So instead of me saying 3 plus, just like me here, instead of me saying 3 plus, I'm saying Al N plus. Like, I don't really know. You get what I'm trying to do here? So we have N E minus. So you know that if it was 3 plus, it means that I would say 3 electron minus. So I'm replacing this 3 with N. Do you get it here? Right? So equal to what? Sn. So like, that's first step. Like, that's first step. That's first step. Do you get? So meaning that N Faraday, right, will deposit what? N Faraday will deposit 1 mole of this guy, or 1 mole of what? Of tin. Is that very clear? So 1 mole of tin. All right. So let's make progress. So from this, we know that our mole is equal to 0.224, right? 0.224 mole. First off, right? That's our mole. Okay. What of our charge, right? So we are given T, yeah, the quantity of electricity passed. This is 4 hours times like 60 times 60. You get, so we have our Q, so we go to IT, our I is 3, our T is times 4 times 60 times 60. Exactly. 3 times 4 is 12. 12 times. Please, use your calculator, please. What's the answer? Yeah, 43,000. 43,000, how about 43,200 columns? Yes, for 3,200 columns. Now, to make things really easy, I would like to give it a fraction, more like a fraction of Faraday, right? A fraction of Faraday. So meaning that if 1 Faraday is 96,500, right? X Faraday would be 4,000 for 3,200. So I just have to just divide it. I just have to just divide it, which is for 3,200 divided by 96,500, right? So 96,500, please use a calculator. You're able to get 0.45 what? Faraday. Okay, 0.45 what? Faraday, first off. Exactly. So we now know that 0.45 Faraday, 0.45 Faraday, right? 0.45 Faraday will liberate what mole? 0.224 mole. Did you get? Don't worry, I'll explain again. But did you get it, Sha? Okay, now cross multiply. We have 0.45 Faraday is equal to 0.224 times n Faraday. So, right? We're trying to get n, right? Okay, so we now have Faraday, we can have Faraday, right? So have n is equal to 0.45 divided by 0.224. So what's the answer, please? Approximately correct. Approximately 1.2, approximately 2. Exactly. So our answer is what? Plus 2. So plus 2. This is our final answer. Now let me explain again for those who might have been lost. Okay, we've been told to get the oxidation state. We don't really know what it is. Like we don't really know. Unlike aluminium, which is 3 plus, and we don't really know. So, but it's still the same average. So instead of me using 3 Faraday equals to 1 mole, I just say okay, n Faraday will give rise to what, 1 mole, right? So, this reaction was taking place. We have our charge, we have our time, right? So meaning we can get Q, like we can get Q and know what it liberates. It deposits, look at the word it said here. Deposit 26.6 gram. Do you get? It deposited 26.6 gram. Now, just use your n, right? So which is what? 26.6 gram divided by what? Yes, very molar mass of tin, which is 109 gram. Exactly. So that's how I arrived at 0.224 mole. Now, in order to make this in unison, I don't want to say n times for in this part. Like I don't want to say n times like n times 19,500. It makes everything clumsy, and there's really no time. So you have to find a way of cutting these down long processes. Now, I just have to divide 43,200, right, which I obtained from the Q here, as you can see, right, 43,200 divided by 96,500. So I arrived at 0.45 Faraday. So 0.45 Faraday is what gives rise to what? This guy, Diget, which is this, Diget. So now cross multiply your normal way and use the calculator, you should be able to get arrive at this answer. All right, the last question for today. All right, very fast. Today's video is longer, but then it's worth it. Yes, why not? Okay, so now what would be the concentration of copper sulfate in solution after 4 ampere of current was passed for 1 hour through 500 centimeter cube of a solution that was originally 0.2 molar or 0.2 mole per dm cube, right? So it's very easy. If you really understand stoichiometry, this will be really, really easy for you. Like, damn easy. Damn easy. Okay, now, what about current? What about current to be 4 ampere? And what about time to be 1 hour? So, like, 1 hour and 60 times, like, so, like, this is like 360 seconds and less like that. Okay, so, yes, so what of Q will be 4 times this, so you will get 14,400 coulombs. Now, as a principle, I like breaking down stuffs. So we have to check it, we have to make it relative to Faraday. So just divide this by what? 96,500. Exactly. What you're going to arrive at, if you click in your calculator, you're going to arrive at 0.149 Faraday. Exactly. Now, the discharge of copper ion in solution is actually represented by this reaction, right? Yeah, it's represented by this reaction here. Do you get? So meaning that 2 Faraday, right, will deposit 1 mole, right? 2 Faraday will deposit 1 mole. So 0.149 Faraday, that's from here, right? Will deposit what? How many mole? Hmm. We don't know. We don't know, but we have to calculate it to get it. Do you get? So cross multiply. We have 0. This is just x. So let's say x is equal to 0.149, right, Faraday divided by 2 Faraday. Faraday cancel Faraday. So just divide it. Just divide. What do you get? Yeah, 0.075 mole. Is that clear? So 0.075 mole of copper was deposited. Do you get? Now, here's the twist. Now, this is mole, right? So we have to try and get mole from this, the original mole. This is what was liberated. It's just as if there is a large bread, right? That's a large bread. So this is the initial. Do you get? So this was given to the dog. This part was given to the dog. Now this part was remaining. This is what we were told to find. Together, this is what we're told to find. Now, you see this part. You see this part. This is 0.005 mole. 0.05 mole is this part. Exactly. Meaning we have to know the whole stuff. We have to know, we have to find a way of getting the whole stuff. Is it get if we have to get the correct answer. Now we have been given something really important, concentration. We'll also be given volume. Volume does not change. Volume is constant, right? Like yeah. So now there's this formula in stoichiometry which is N is equal to CV. Like very simple, right? So the concentration is at 0.2 molar. Uh, there's only have to take note of dm cube. So 500, right? So to convert centimeter cube to dm cube, how do I say you're going to approach it? Divide by 1000. That's simple as that. Easy peasy. So divide by 1000. So this is cancel this, this cancel this. So this like yeah, this like go back one. That's like 0. What? So 0.2 times 5 is what? Yeah, 0.1, right? Right, 0.1, 0.1. Is that very clear? Is that very clear? Okay, so that's 0.1, 0.1 what? Mole. This is the initial. So meaning we have to get this, right? But what we're working with is actually mole. So let's just get it. This is the final, right? So to get x, I'll subtract this from this, right? So x is equal to 0. Sorry, sorry, 0.1 minus 0.075. So what's our answer? 0.1, please have a calculator. 0.1 minus 0.075 is what? 0.025 mole. Is that very clear? So that's our n. Is that our final answer? No, it's not. It's not. We're trying to find concentration, not mole. Exactly. So you have to now go back. Do you get? You have to go back to get this in right. So n is equal to CV. We know that for a fact. We've gotten our n. We know what our volume is. Just make C solve the formula, which is what n, which is 0.025, right? Divided by our v. What's our v? 500 divided by 1000. That's like 0. Like half. Like it's like 500 divided by 1000. You get just in calculator. What to be fast. So what's the answer? What's the answer? Yeah, 0.05 mole per dm cube. Do you get? So this is our final answer. 0.05 mole per dm cube. Okay, yeah, that's all for today. So I don't know if I have to go over this particular one. I think I've explained it very well. So thank you so much for staying up until this moment. I'm really grateful. Thank you so much for watching. Ensure you subscribe. Yeah, share the video now. Yes, share to your friend. Ensure they benefit from it. Thank you and God bless you. Bye.